As we have discussed so far, in its chair form has 6 axial bonds and 6 equatorial bonds. And all the axial bonds which are looking upward are called beta axial bonds. And these 3 axial bonds which are looking downward are called alpha bonds. So there are 3 beta axial and 3 alpha axial bonds in cyclohexane. Likewise, there are 3 alpha equatorial and 3 beta equatorial bonds. So the beta bonds are the ones which are looking upward and the alpha bonds are the one which are looking downward. When the cyclohexane undergoes ring flipping, all the axial bonds will become equatorial and all equatorial bonds will become axial, but the alpha bonds will remain always alpha and the beta bonds will remain always beta. Now let us see how the ring flipping converts all the axial bonds into equatorial and equatorial bonds into axial. This is the cyclohexane chair form. The 4 carbon atoms in the middle are lying on the same plane. This carbon is above the plane. Now this looks exactly the chair. Ring flipping is not the mere rotation of the molecule. Instead, keeping the middle carbons in one plane, we are bringing the down carbon up and up carbon down. That is called ring flipping. The down carbon is brought up, the up carbon is brought down. Now, all the axial bonds are converted to equatorial and all equatorials are converted to axial. And this becomes very obvious now when we insert a ball here. I have inserted a ball in the axial position and then now I am doing the ring flipping. When we do the ring flipping, the ball which was originally present in the axial position has now occupied the equatorial position. Therefore, the ring flipping of the chair form of cyclohexane converts all the axial bonds into equatorial and all equatorial bonds into axial. This is the boat conformation of cyclohexane. This has 4 types of hydrogen atoms. These hydrogens 1, 2, 3 and 4. These hydrogens, the 4 hydrogens which are looking down, these are boat axial hydrogens or they are called quasi-axial hydrogens. 1, 2, 3, 4. These 4 hydrogens which are denoted here as QE are quasi-equatorial bonds or the boat equatorial CH bonds. Apart from these 8 hydrogens, we have 2 hydrogens here. These are called flagpole hydrogens. And there is a steric repulsion, there is a repulsive interaction between these 2 flagpole hydrogens, which increases the energy of the molecule to a considerable extent, and that is how it is destabilizing this conformer. Apart from these flagpole hydrogens, we have the 2 hydrogens at these 2 ends, which are denoted as BS. They are called bowsprit bonds. These bowsprit bonds are going away from the ring. And in this boat conformer, there is flagpole interaction that raises the energy. Apart from that, there are eclipsing interactions between the axial hydrogens, these 2 axial CH bonds, these 2 and these 2 and these 2 will have eclipsing interaction. In a similar way, there are eclipsing interactions between the equatorial bonds. These 2 are eclipsing, these 2 and these 2, these 2. So there are eclipsing interactions between the axial and equatorial CH bonds, which are also responsible for the rise in energy of this conformer. That is why this boat conformer is having higher energy than the twisted boat. This boat form has a C2 axis of rotation at the center, and as we have discussed, there is flagpole interaction, eclipsing interactions between axial and equatorial bonds. Apart from all these repulsive interactions, there are 4 Gauss-butane interactions present in this molecule. You consider this carbon as 1, 2, 3, 4. If you consider this portion of the molecule, this looks like N-butane, where with respect to this CC single bond, these 2 bonds are having Gauss-butane interaction. Likewise, just you consider 1, 2, 3, 4, and in this part of the molecule with respect to this carbon-carbon single bond, these 2 bonds can be rotated, and in this boat form these 2 are having Gauss interaction. Likewise, there are 4 Gauss-butane interactions which I have mentioned here. So the Gauss-butane interactions, flagpole interactions, eclipsing interactions, all these repulsive interactions are raising the energy of the molecule, and that is why this conformation of cyclohexane is having higher energy than the twisted boat form. When we try to convert the half chair conformer into boat form, we are going through this conformer called twisted boat or twist boat form. In this twist boat form, the eclipsing interactions are not as in the case of boat form. The eclipsing interactions are reduced, and these flagpole hydrogens are going little far from one another, and because of all this, and the Gauss-butane interactions are also reduced. That is why this twist boat form is having a lower energy than the boat form by 1.6 kilocalories per mole. So we have seen in the boat form there was flagpole interaction, eclipsing interactions, the Gauss-butane interactions. All these repulsive interactions are reduced in this twist boat form. That is why this twist boat form is having a lower energy than the boat form. Now let us see what happens to the energy of the cyclohexane molecule when one chair form of cyclohexane is converted to another chair form. This is the chair conformation of cyclohexane, where these 4 middle carbon atoms are in one plane. This carbon is below the plane and this is above the plane. Now when we try to lift this carbon up, this carbon also comes to this plane, and it is becoming another conformer called a half chair conformer. This half chair conformer is the one with the highest energy, and this has 11 kilocalories per mole higher energy than the chair form. When we try to lift this carbon still above the plane, it gets into another conformation called twisted boat, and this twisted boat is having lower energy than the half chair. And when we lift this carbon still up, we get into another conformation called boat conformer, which is having 1.6 to 1.8 kilocalories more energy than the twisted boat form. Now if this carbon, so far we had been lifting this carbon up, now we shall bring this carbon down. When we bring this carbon down, we will once again go through another twisted boat, a half chair, and then another chair form. This is what happens to the energy of cyclohexane during this ring flipping of one chair into another chair. We will continue our discussions with another topic in stereochemistry. Until then, bye from AMALORPAVADOSS. Thank you.